Hello, I'm Ethan Fish, and this is my CA2 wall insulation project. First, we're going to dive into the problem statement and a couple goals we have. So, problem statement is a 4-meter high, 6-meter long wall is constructed of two large 2 centimeter thick wall steel plates, separated by 1 centimeter thick, 20 centimeter wide steel bars, placed 99 centimeters apart, and that remaining gap between the steel plates is filled with fiberglass insulation. If the temperature distribution between the inner and outer surface of the walls is 22 degrees Celsius, determine the rate of heat transfer through the wall. Can we ignore those steel bars between the plates in heat transfer analysis since they occupy only 1% of the heat transfer surface area? That will be our problem statement. Now we're going to dive into the goals. So we want to determine the heat rate or rate of heat transfer through the wall. We want to determine if it's possible to ignore the steel bars between the plates. We need to model this wall as a thermal resistance network. Find the temperatures at the edges of different materials. Adjust 3 parameters to analyze their effects on this wall. Analyze a different insulation material. And then for the goal of our wall, we want a low heat transfer rate, which results in a colder room while we are redesigning this wall. So here we have the thermal resistance network. On the left-hand side, you can see the initial or complex resistance network. So you see the resistance of the first plate, which is the left-hand side of the wall. Then in the center, we have the steel bars and the insulation. And then next, we go to this of the last plate, which is on the inner side of the wall. That can be simplified down to just the plate, our equivalent, and then the other plate. So for the calculations, they were all done in MATLAB. We found the heat transfer across the wall, temperatures at the edges of each material, and then there's calculations that showed you can neglect the steel bars. You cannot neglect the steel bars when calculating heat transfer across the wall. Here we have the graph of temperature distribution across the medium or the wall. So the graph displays temperature points across the wall. Steel has a lower resistance, and fiberglass is an effective insulator with a K equals 0.035. So this graph here shows the temperature at each point. You can kind of see what's going on there. You can see the big drop between the two steel plates where the insulation and the steel bars are at, right here. And you can see the reference data over here in the bottom left hand in the chart. It gives the temperature at each spot, total resistance, and the Q dot total across the whole wall. Now we're going to go into some of our changes that were made to analyze their effects on the system. Here we changed the thickness of the steel plates, which are on the left and the right hand side of the wall. So as the thickness increased, the heat transfer rate just decreased. You can see that here. Q dot, which is our y-axis, and the thickness is the x-axis. So as this plate got thicker, that Q dot had an exponential change which decreased that Q dot, which is pushing towards the goal that we want to have a lower Q dot heat transfer rate across this wall. Next, we changed the insulation area, or the area of insulation. But with this, we also need to make sure that the thickness of the steel bars was also decreasing as this insulation was increasing. So you can see as the area increased, that heat transfer rate decreased, which is again what we were pushing for with our goal. So that was good to see, and makes it easier to redesign this wall. And then for our third parameter that we changed, it was the K value for the insulation. So we increased the K value, and as you can see there's a linear change with Q dot. So linearly, when K increased, Q dot increased, so which is opposite of our goal that we want. So we want to make sure to redesign this wall, we want a lower K value. Now we want to see if we can ignore the steel bars in the center. Even though they take up 1% of the area, the resistance is substantially less compared to the insulation. which means they cannot be ignored. They're kind of acting as like a thermal bridge. So as you can see here, the Q dot with the bars, heat transfer rate with the bars, and without. And then there's down here is the temperatures as well. So you can see there's a minor difference, but it all adds up. So we need to consider that when analyzing this wall. And then finally, we tested a different material. We tested hempcrete, which is a mixture of hemp herds or shives and lime. So it's an insulator and moisture regulator, but a con of this, it lacks brittleness and is very high density. Here's the analysis of the hempcrete insulation, the temperature distribution across the wall. It's the original parameters besides the K value, which is 0.06, which is an increase from the fiberglass, which as you can see from when we changed the K value in our parameters, that was not what we were looking for. So this is not a beneficial insulation that we would want to use. You can kind of see that down here too, that Q dot is much higher. So for our redesign, we want to look at multiple things that are in consideration, such as the material, thickness, etc. So as a goal to lower the heat transfer rate, keeping the inside of the room at a lower temperature, we would want thicker plates to achieve the goal. It will give us a lower heat transfer rate to prove to have more insulation. The type of insulation we will want to choose will be based on the K and R values, smaller K value and a larger R value. And then we would also want to eliminate the steel bars within the wall because those would not be beneficial for our goal. Thank you.